Here we have challenging trigonometric problems, and so the first one states that tangent of 3x, and we squared that result and we get 3 here, so that's the equation. Now again, the first step would be, because we see 3x here, right, so we say that this is some variable, so let us say this is just equal to z or something like that, so 3x is equal to z. So now we're really saying that the tangent square of z is equal to 3 really. And so when we look at this, we should understand that the tangent of z itself, because we really take its square root, so the square root of this is equal to the plus or minus square root of 3 really. Because obviously we're not just taking the principal root of 3, we're also taking the negative root 3, because we have tangent square, so we obviously have to take the plus and the minus, the two roots here. So we would say the tangent of z is equal to root 3, and then tangent of z is also equal to negative root 3. So we have two equations here that we have simplified to. And now when we look at this, clearly we should know, although it's on the unit circle indirectly, if you memorize all the key ratios involving tangent, you should understand that z in this case could equal pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And so these are the values that we get. And really, why? I mean, if you haven't memorized it, obviously what you can do is you can do sine of pi over 3. So what's sine of pi over 3? Sine of pi over 3 is root 3 over 2. And what's cosine of pi over 3? Cosine of pi over 3 is 1/2. If we're dividing by 1/2, we're really just multiplying by 2. So the 2 and 2 cancel off, and then we're left with root 3, which is what we have here. So obviously pi over 3 is one value. So if it was only the principal root of 3 or the positive root of 3, we would be looking at pi over 3 and then the third quadrant value, which would be 4 pi over 3. Again, because again the rule is the numerical value in the numerator is 1 greater than, or is 1 more than the numerical value in the denominator, right? So we would have pi over 3 and 4 pi over 3 as our answers. However, we also have this negative root 3, which really means that we're looking at all values in the quadrant. So really we're taking each value, one value from the first quadrant, one value from the second quadrant, one value from the third quadrant, and one value from the fourth quadrant. These are your two values, 2 pi over 3 and 5 pi over 3, that correspond to this negative root 3. However, in all these four angles, if you look at it carefully, you see that pi over 3 is the reference angle that we're looking at, because tangent of pi over 3 is equal to root 3. So these are the four values. And now why I said this is challenging is because again we use that same concept. So we see that pi over 3 plus 2 pi n, that is equal to 3x, right? Because that's what we had originally. Again, it's the same idea, and we would do 2 pi over 3 plus 2 pi n is equal to 3x, and so on with the other ones. 4 pi over 3 plus 2 pi n is equal to 3x, and the last one would be 5 pi over 3 plus 2 pi n is equal to 3x. So we have these, and obviously now we really end up dividing all of these equations by 3 to isolate x. And so after we do this, we get that x is equal to pi, so you would divide, so you get x is equal to pi over 9, right? Plus 2 pi n divided by 3. Right, and we think about this, again, you could multiply this by 3, so you really have 6 pi n over 9. Looking at this one now, the second one, we can again divide both sides by 3, so we get x is equal to 2 pi over 9, and then we have plus 2 pi n over 3, and that's really just, again, 6 pi n over 9. So this is what we have here. And then for the third one, we have x is equal to 4, I believe 4 pi over 9, right? Yes. We divide, again, this by 3, so 4 pi over 9, plus 2 pi n over 3, right, which is really, again, just 6 pi n over 9. And then for the fourth one, we would get x is equal to 5 pi over 9, plus 2 pi n over 3, which is 6 pi n over 9. And then obviously, because it's 9, you get the idea that it will be pi plus 6 pi n all over 9, 2 pi plus 6 pi n all over 9. Same idea, because we have that common denominator. I just don't have enough space to write that, but these are the four different equations we have, really, and we have this in terms of x. So now when we want to find our final values, I'll just erase this here quickly. So this is what we got. We will be substituting integer values in for n. And so if we do this, right, again, and that's why I had mentioned, again, this restriction here, 0, 2 pi, so it has to be the x value, or the value that you're determining for x has to lie within this, obviously. So when we are substituting values in for n, we have to be careful that it lies, or it falls, or it abides by this restriction here, 0, 2 pi. So now we really just substitute values in. So the first value you always want to substitute in is 0, right? So 0 really means that all of these are gone. So essentially we're left with pi over 9, right? So our solution set here, right? All the values for the equation. So we have pi over 9. We have 2 pi over 9. We have 4 pi over 9. We have 5 pi over 9. So these are the first 4 values we get. And really, we're going to now plug in 1. So if we plug in 1 here, we get 6 pi over 9 plus pi over 9. That's 7 pi over 9. We do the same thing here. We get 6 pi plus 2 pi. That's 8 pi over 9. And for the third one, we substitute 1 in. We get 6 pi over 9 plus 4 pi over 9. That's 10 pi over 9, right? And then so we have this, right? And then we can do the same thing here. So we have 6 pi plus 5 pi. That's 11 pi over 9. And so now we have gone through all of the 4. Now let's try another cycle if it's possible by substituting the integer value of 2. So if we do this, right, we plug in 2 here, we get 12 pi over 9 plus pi over 9. That's 13 pi over 9. Again, doing the same thing here in the second one, you would get 14 pi over 9. And then doing it here, you would get 16 pi over 9. That's a lot. And then your final answer would be 12 pi plus 5 pi. That's 17 pi over 9. So we essentially have, I believe, we have 12 values here that satisfy this equation. And so clearly the fact that when we had the original equation had tangent square of 3x, right, that square caused us to have root 3 and then a negative root 3, which obviously caused us to have many more solutions than we had originally expected. So that's the first problem that I wanted to go over. So that would be the solution set. Now looking at this second one, this one's quite interesting as well. Because in this one, when we look at this, so we have an equation, right? We have tangent of x plus secant of x minus 1 divided by tangent of x minus secant of x plus 1 is equal to tangent of x plus secant of x. Do recommend you to pause the video and try this on your own at first. However, this one is a little bit more complicated. You really do have to think Exactly, because again, we're not really solving. Again, what we're trying to do is we're trying to prove that one side is equal to the other side. That's the idea of this problem here. So really, we're just proving the trigonometric identity here. So looking at this, really, what happens is we tend to really disregard this one, and this is really important because if you don't look at this one, then you probably can't solve this equation. Usually what people are going to do is they're just going to discard, or they're disregarding the one value. But if we think about it, our equation, right, we have the equation or the identity here. Let me just write it here. We have 1 plus tangent square x is equal to secant square x. This is the Pythagorean trigonometric identity that we know. So when we have 1 here, right, we are really saying that this is the same thing as saying secant square x minus tangent square x is equal to 1. And so this is important in this case because this is exactly what we need here. So if we know that this is equal to 1 here, clearly we can write that here. So we have tangent of x plus secant of x minus secant square x minus tangent square x, because this is essentially just 1, right? That's just 1. So now we have this clearly, and looking at this, if you recall that this is really in the form of a squared minus b squared. Now anything in the form of a squared minus b squared can be written in the form of a plus b times a minus b, right? That's the other identity, I guess you could say, the algebraic identity. A squared minus b squared is equal to a plus b times a minus b. So we can split this up further, right? We could say tangent of x plus secant of x minus, what we're really saying is secant of x plus tangent of x times by secant of x minus tangent of x. So we have this here. Now if we think about it, there's something really interesting here. The thing here is you obviously have you split this up here like this, but the thing here now is you can really factor a value here. If you look at this, this is tangent x plus secant x, right? And then you have tangent x plus secant x here too. So why not put secant x plus tangent x, and really you have this here, so 1, because you're factoring this out. So you secant x plus tangent x times 1 is this. And now you're going to do minus, right? You're going to do minus secant of x minus tangent of x here, because you have this times by 1, right? And you have minus this being multiplied by this, as you can see here. I think what I've done is I forgot this denominator value on the bottom. So just assume that in each of the following steps, I have tangent of x minus secant of x plus 1 on the bottom here. So we really had it here, we have it here, and we have it here. And same thing with this one, so we're just continuing this forward. So now we get this, right? And really on the bottom, we had tangent of x minus secant of x plus 1, and obviously we have here we have tangent of x plus secant of x. Again, just carry the denominator value in this below, so you get the idea here. You have this and this. Now when you look at this expression here, 1 minus secant x, and then you have minus plus tangent x. This essentially is really just this. So really we're seeing that this and this completely, they're gone. This and this are gone. So we're really left with secant x plus tangent x is equal to tangent x plus secant x, which is essentially the same thing. So really, again, when we're solving or when we're simplifying these expressions, we are keeping one side completely the same. Again, here we thought this side was simpler, so we just extended this downwards, as you can see here, and we just keep this here, and we changed the more convoluted form and simplified that so that we could equate this to this, or make this look like this. And here we have done that. So again, it's just important to understand that 1, whenever you see that 1, you may want to try to just alter that so you can bring it in this form, secant square x minus tangent square x. So thanks for watching. These were some of the more challenging trigonometric problems.